on this computer. All right, hello everyone. I am still going to try to record this. We'll see what happens. I'm using this computer instead, so it'll see the slides, but I don't know if it'll show me at all. We'll just give her a go. There's another program I like to use for this, but I'm not allowed to install anything on this computer. But if this doesn't work out nicely, we can do it for next time. So let's see. Did you notice your grades up on Blackboard? Probably. Okay. Good. I still need to send out the rubrics. Write down a note. I did do those. That's where your grade comes from. But I'll email out the rubrics. But overall, I was pleased with the presentations. I feel like my expectations were a bit higher, and I felt like y'all did better than even last week on my expectations. There's a condom down there. That's interesting. Well, I guess that's recorded forever. Cut out the start of the video. So that was good. I like seeing all of your presentations. There's a little bit of feedback in the rubrics, but I wanted to talk about some general comments and some changes for our next presentation. So I thought overall, in general, some of you could have less emphasis on the method section. So I know we're crunched for time, and I thought there could be less detail in the method section, and I wrote down some notes about this to give you some examples.
I had a question about that. I feel like some people talked about process, like the actual process of our data processing.
Yeah.
And some of us didn't.
Yeah.
And we're going to do those processing going forward, right?
Yeah.
So do we need to talk about that?
I think much of the data processing probably isn't needed. Let's see, I have an example here. So important in so part of the processing, I think you should say, hey, we're calculating mean reaction time. So that lets people know, hey, what are these values we're seeing later? It's mean reaction time. So I think that's important. Not important, I would say that you remove practice trials and bad trials. So if you were writing a manuscript, you would put all those details in there. So you have to have it detailed enough for someone to replicate the experiment, and that's important. But I don't think it's so important that it needs to be in the presentation. And I understand this is a fine line, and I haven't to this point kind of docked marks for saying, oh, that's overly detailed, but that is actually a change for our next round, which that's why we're talking about it now. Something in the middle of those two where I could see maybe you included, maybe you wouldn't, because some of this is judgment, personal preference, is like that we excluded trials for these figures. That because if someone, I could see that coming up as a question, like, well, maybe it's slower because you're including more figures. And it's like, well, we control for that. That's kind of in the middle category. And this is hard, and it takes some time and experience, and maybe from watching your peers, you can be like, oh, that was very detailed, or someone else, oh, that wasn't as much detail. How do I feel about it? So you can kind of think about it on your own. But that's my impression, that the method doesn't have to be as detailed. So the 4 sections of the presentation, intro, method, results, discussion, you kind of think of them as being equally important. So you don't want to have 3 minutes on method and then 30 seconds on the other sections. Another example, so I mentioned this once or twice. So important, describing the trial sequence in one condition. So you're sitting there, the lights come on, you press a button. That's good. That's fundamental. But you don't need to describe the exact trial sequence in every condition. So once you've described one condition, you can then kind of summarize. A lot of people have that good summary slide where, like, yeah, we did simple left, simple right, 2 choice, 4 choice, 8 choice. Moving on. But for one of those blocks, you can show exactly that. Well, this light turns on, you press a key, but you don't have to do that detail 5 times. So this, I appreciate that this is hard. It's kind of like, it's almost easier in a manuscript when you just have to say everything you did. It's like, well, just say everything you did, don't leave anything out. But here it's, it's kind of, what's vital and what's not. So hopefully that helps a bit moving forward.
What do you call Dr. Bunch separating the trees from forest from the trees?
Yes, actually, I wrote that down here. That's but yeah, I want you to tell me about the forest and not every individual tree. Thank you, Lee. So where there sometimes be less emphasis on the method, I think for several people there can be more emphasis on the discussion. And I think it's also because that's the hardest section generally. So, the intro, we learn about a concept, you're telling me about that, the method, well, this is what we did, the results, here's the data. But the discussion is kind of where I'm then challenging to say, okay, well, why is this data like this? And I think a lot of people did a good job. So the discussion in the rubric, there's 3 parts. There's like returning to the original hypothesis, and I felt that was done very well. So I think almost everyone, or maybe even everyone, said, okay, well, this is what happened, and it was as predicted, for example. And then the second part is kind of comparing it to previous research, and there was good examples of that, like when you had the class data and your data on the line graph, that was a good comparison. Some people compared it to Fitz's 4, Hick-Hyman's data, or those 4 charts. And you don't have to do any of those specific ones, but you have to do some. And then the last part, I think, is the hardest and maybe the least well done. That was the interpretation. So excellent in that category is providing a justified interpretation of the results. And 2 examples come to mind. There were more of these, but as I was biking in, there were 2 that were memorable, I suppose. So Guy's example about, well, maybe I'm faster than some other people because I play a lot of video games. And Mackenzie's example of, well, maybe 8 choice didn't work out because of my fingernails. So both of those are interpretations, and I'm not here to say that one is right or one is wrong. I just want you to have some sort of interpretation. I mean, it can't be ridiculous, but some sort of interpretation. What was the third one here? Yes. Sorry, any questions about the discussion section there? So maybe just think about that a little in your next presentation. And also, I mean, hopefully you'll get your rubric digitally today, and you can see. I mean, maybe you're already doing great there, but if not, then consider these points. So I'd like to see more presentations closer to 5 minutes, and to encourage that and these other things. The rubric has been updated. It's now on Blackboard, the new version. And these are the changes. So in the method section, before I said like excludes too much information, but now I say includes or excludes. So I don't think anyone's been saying too little, but we definitely have it's like, a little too much. So that's now in there. Results. Oh, in this round, in this module, you're only actually going to present your own data. So in the rubric, there was your data, class data. So I got rid of class data. That's not relevant. I will, however, still email out the class data. And in your presentation, if you want to refer to it, that's fine. As one of those potential comparisons. You don't have to, but you might decide to. Either is actually okay, as long as you have some sort of comparison. You might refer to the class data. You might refer to the data from the readings. That's up to you. And then the third thing is there's now a time section. So for excellent, good, fair, and poor, those are the thresholds. So if it's on the border, like if it's exactly 440, then I would give you the benefit of the doubt, and that would be excellent rather than good. I guess I could have said 439. I always feel weird about that though. I don't know why. So yes, definitely make sure practice. Make sure your timing is good so that you're in this 40-second window between around 5 minutes. Questions? So raising the stakes a little bit with the evaluation.
So You could go from 40 to 440 all the way up to 520.
Yeah.
And it'd still be X.
Yeah.
Okay. Oh, I see what you did. I see what you did. As you increase the board, like the extremes, you start losing point.
Yeah, I don't know if this was the best way to show it. I guess I could have shown a time continuum and been like, excellent, good.
Yeah, it's just a little hard to
Fair.
see, but yeah.
And on the rubric, it's actually even another way that's maybe even worse. So, but that's the idea. All right. So let's talk about stimulus response compatibility. There was, I think, a good amount of reading in the sample from the textbook about this. So I won't reiterate all of the theory, but I will touch on some stuff that the textbook didn't. And I'll talk about data processing. And I'm hoping today we can even just go ahead and do the demo right here. Because last week it would have been nice if it all fit in that one class and, you know, drag everyone back just for 10 minutes on the next day. Plus, we're pretty used to how the computer works, and it's very similar for this study. So we're talking about stimulus response compatibility. One of the definitions, I think this one's in the textbook, it's the degree of naturalness between a stimulus and a response. So why is that important? And the textbook definitely took the second approach that we'll see here, but so today I'll share a little more about kind of the first approach, which actually, you know, it was hinted about in the textbook. So first of all, there's applying stimulus response compatibility to the field of human factors, sometimes called ergonomics. Human factors might be the newer term, but they kind of both exist and they're mostly synonymous. And nice short definition for human factors, it's the design and engineering of human machine systems for the purpose of enhancing human performance. And the textbook did talk about Paul Fitts. Remember the study with the 3 types of stimuli that were like circle or square, and then the responses with the stylus. So that experiment was a very early experiment by Paul Fitts on how much better you are if the stimuli matches the responses. And he took that very basic knowledge and then applied it to aviation safety. And this was post-World War II. So pre-World War II, you know, 40s and earlier, there wasn't much consideration given to how do we design products so that they're natural for humans to use, which I think nowadays maybe seems like kind of obvious that we would do that. And, you know, Apple is a great example where they invest a lot of money into making their devices very compatible and very user-friendly. But pre-World War II, there wasn't a lot of consideration given to that. Paul Fitts served in the military, I think in the Air Force, and he felt that a lot of the lives lost, you know, in the airmen weren't to say, you know, enemy fire, but to poorly designed aircraft. So after the war, he got into this field and really pioneered aviation safety. And this idea of human factors has spread to many areas. Automobile safety is another big one. Not just airplanes, but military in general. So I actually worked for a military contractor for a co-op work term. And it was the whole idea was, okay, you know, how do we design this product so that often you have to think of the extreme. So think of a soldier who's highly fatigued, highly stressed, and now needs to perform this duty, and they need to do it successfully without, you know, killing themselves, killing a teammate, and they have to do it and potentially kill an enemy. So it's a very stressful workplace, right? Compared to our daily lives. So it can be even, you know, extremely important in those situations. So we'll talk about just a few of those examples because the textbook didn't talk much about it because arguably it's a whole nother area of stimulus response compatibility. What we'll come back to and the textbook focused on, and what we're going to focus on in our experiment is using stimulus response compatibility as a cognitive psychology method. So we want to use it to get theoretical insight into how response selection works. And we're going to look at kind of the simplest example of compatibility. It's kind of the simplest experiment, and yet it has a very big compatibility effect. So just a bit on human factors. So it really is, it's such a big area. It's kind of its own field of science. In a lot of places, it falls under engineering, as it does. Oh, no, it doesn't at Tech, does it? It falls under psychological sciences. Sorry for my confusion there. So some universities, it's engineering, some it's under psychology, and usually the people within it, though, can have both approaches to this area of research. So there's a whole group at Texas Tech that focuses on this type of research. So a few examples, I mean, from what I talked about earlier, there's some very extreme, important examples, you know, that can determine whether you live or die. And then there's also just the silly examples of things that you might find frustrating in your daily life. And for me, I hate USB type A. I guess I also hate USB type B. You don't see it that often because it only works one way, right? So when I come and plug in my USB flash drive here, it'll only fit this way, it won't fit the other way. And that's annoying. I mean, I'm not going to die if I don't get it right. Class might be delayed a few seconds, but USB-C, which is newer, and Lightning, which is newer, they're reversible. So it doesn't matter, both ways are up. You know, you do it this way or that way, it works. And that's, you know, just a very simple example of designing something better that is, you know, more user-friendly. It's more compatible. Another good example, the QWERTY keyboard. Does anyone know why the keys are arranged in this manner?
I think it's because the typewriter used to be.
It is, yeah. So the history behind QWERTY, there's some arguments about exactly what happened. I'll give you the popular tale. It does have some support to it, but there are kind of variants of this story. So yes, it's called QWERTY because the QWERTY, they're in a row. And yes, keyboards, typewriters before keyboards were also laid out like this. Now, with a mechanical keyboard, so you have a mechanical typewriter, so the latest typewriters were electronic. Before that, they were mechanical. I guess I should have one so I can show it. It's before my time, but what happens is you press a button and an arm comes up, hits a ribbon of ink, your page is behind that, and it leaves the letter on the page. So it's like a piano. It's as mechanical as, you know, hitting a piano key and it hitting the string. The problem with mechanical keyboards, when they first brought them out, you know, no one was good at typing. You can imagine if you remember being a child, but that would be adults all of a sudden being like, oh, here's a mechanical typewriter. You're like, oh, okay, how does this work? Everyone was slow, but it didn't take long for some people, especially people who were typing all day. They got fast. And the problem with mechanical keyboard is if you press two keys quickly enough, they jam together, and they're stuck. You know, you've made a mess of your paper. You got your finger in there. You probably get all over your finger. You might need to start over. So it was a problem. So I said, okay, well, people are typing too fast for these keyboards. What do we do? Enter QWERTY. They said, let's put the keys in a way that's very inefficient for typing. That'll slow people down, and then the mechanical keyboards won't get jammed up. So that's what they did. So these numbers here, they say 30, and this would be for English, but 32% of your typing is in the home row. So that's, you know, where your hands are resting. And you would want most of your typing to be in the home row, because the further you have to move, the slower it is. So I said, okay, well, let's move some of the important keys further away, like E, the most common letter in the English language. To hit it, you got to reach, so that's going to slow you down. So 52% of the time you have to reach up, that'll slow you down. There's even slightly more typing in the QWERTY keyboard with the left hand than the right hand, which would be inefficient for the majority of people who are right hand dominant. Is there a better keyboard? Yes. People still research this, but one common one is probably, I think even Windows, it used to support it, I'm guessing it still does, is Dvorak. Now, Sadly, Dvorak is the name of one of the co-inventors. The last name, the keyboard doesn't spell Dvorak anywhere, which would have been nice. So they said, okay, well, let's rearrange these keys so that most of your typing is in the home row. And you can see here, there's E, and you got some of your other vowels, which would be used a lot. And this keyboard, you do slightly more typing with your right hand than your left hand, which is also beneficial. You might think, oh, maybe E should be on the right side, but maybe they were trying to put all the vowels together. Maybe that's easier for your head. I don't know. So this is a faster keyboard. And when I was in software engineering, some of my friends actually used it because they're like, well, it's faster, it's better. Why haven't we all switched to it? It's better. It's definitely better. Well, what they've looked at is, let's say January 1st this year, we decided to switch. Goodbye QWERTY, here comes Dvorak. Well, there's some problems, right? We'd be really slow because we're used to one thing and we got to do something else. So we'd be less productive for a while. Also, we'd have to go and replace all of these or get, a new mat that changes all the letters. It wouldn't be as bad for a cell phone that has, like not say a BlackBerry, but an iPhone where it's just electronic and you could change it, but you would still be slow for a while. And they've argued that the cost to switching is larger than the cost we would gain from being a little bit faster. So that's the argument for why no one has tried to say, okay, we're all going to use Dvorak, which is, I don't know if there's a similar argument for metric and imperial, but there, if we all switch to metric, there would be a cost to that as well. If they're ever going to make it work, what I think they need to do is say, at some point with a new generation, just say, okay, these children, when they go to school, they'll learn Dvorak. As they get older and older, they'll use it, and all of us QWERTY people will die. That's probably the best strategy. Anyways, there's a couple of fun videos that I show in my undergrad class. We won't watch these, but if you want to check them out on YouTube, they're quite fun. So design of doors, bad doors are called Norman doors, after Norman, a famous human factors individual, who's, I believe, still alive, not as old as Paul Fitts. Paul Fitts has passed away at a young age, actually. Roundabouts. So this is one I talk about in my undergrad class now because there's a new one on campus, and every year we get a few more in Lubbock, or maybe one or two each year. So it's an interesting topic. But the one I will mention, maybe my favorite example, is how poor stimulus response compatibility led to George Bush winning the 2000 presidential election against Al Gore. Do some of you remember this election? Oh, Guy remembers it well. Yeah?
Yeah, it's a big deal.
Were you in Brazil at the time? Oh, okay, but it was still in the news.
Yeah, they made a lot of jokes about it. Like, there were a lot of internet videos where people try to play one on Al Gore, and in the end, just like remember that I thought this was good. And that's why they couldn't vote for him.
So it was a controversial election, more controversial than this past election. So in my undergrad class, a lot of those students, they were, some freshmen would have been born when this happened. So this is a while ago, but a lot of people say, oh, Trump and Clinton, wasn't, there's no Clinton and Trump, is that?
Yeah, that was in 2016.
Oh, Biden.
The guy who's there.
Well, yeah, I guess both of those were kind of controversial, but I guess Trump and Biden kind of lives on with all of the recounts. Anyways, we won't get political, but we'll say, it's in the news, right? Well, this one was even more of a mess up. It was so close. That was another difference. It was such a close election that it came down to who won Florida. And whoever won Florida would win, have enough seats to win the presidency. So Florida was critical. Now, unfortunately, they had a very poorly designed voting system in Florida. And has anyone actually voted with a non-electronic system before? They've tried to get rid of these, and this is one reason. So here, what would happen is you would come in, and this is a piece of paper, and here there's holes that you punch. And there would be instructions that tell you, if you want to vote Republican, so it has the two names, Bush and Cheney, and that's going to end up winning, you should punch hole number 3. It's got a nice arrow there, and it seems relatively straightforward. The problem was that the narrow of victory was small. So Bush beat Gore in Florida by 1,784 votes. It's not a lot, right? And that secured the victory for him. However, when you look at the number of invalidated votes, it was much larger than the margin of victory. Now, why? Invalidated votes were probably mistakes. I don't think there's many people who go to vote and purposely invalidate their vote. I mean, maybe as a form of protest or something, maybe go in and punch every single hole. But there were a lot of people who punched 2 holes. And you also need to keep in mind that Florida, as the stereotype suggests, a lot of old people live there. And things like a fatigue stressed soldier, where even simple decisions become harder, we also see a parallel in aging. So we need to design things as intuitive as possible, not necessarily for the ideal situation where it's easy, but for those extreme situations. So what happened here? Well, 1,631 people invalidated their vote because they had punched 2 holes. So who are they probably trying to vote for? And I mean, we can only guess, right? But I would say they were probably voting Republican, and they said, well, there's 2 names, so I should punch 2 holes. Or maybe they were trying to vote Reform. You could probably argue that most of these people were voting Republican because within the US, those 2 parties get the vast majority of the votes. So yes, maybe a few of these people were trying to vote Reform, but in general, not many people vote, workers' world or natural law. So I wish I had better percentages for how many people in Florida actually voted for those parties, but it would be very, very small numbers. So let's give Bush the benefit of the doubt. We'll say those were his votes. Now, a lot of people punched those 2 holes, 5,330. It's a lot of invalidated votes. And I'm going to say they're probably trying to vote Democrat. Maybe Reform, maybe Socialist, but not many people vote for those parties in general. And then a lot of people punched holes 5 and 6. Probably were also trying to vote Democrat, maybe Socialist, maybe Libertarian, but I don't even know what those parties are. So probably not. That was another almost 3,000 votes. And when you add all these up, so yes, Bush probably lost out on some votes. Gore probably mixed out on even more votes. And in the end, that would have given the victory to Gore by far more votes than the initial victory. So it's not a great design. Obviously, you want someone to come in, quickly understand, make a selection, and vote for the proper person that they intend, and definitely not invalidate their vote. So not a great compatible interface between the user and the voting mechanism. So any questions about kind of human factors side to this before we move on to what I guess is more applicable to our experiment? So the task that we're going to look at, the experiment we're going to run, is going to involve 2 choice reaction time, which I guess we've seen twice now with Donders and the Hick-Hyman law. So we're all very good at this. The idea is that if the left light turns on, you press the left button, and if the right light turns on, you press the right button. The other name we call this is the ipsilateral mapping. So ipsilateral meaning same, and lateral for side. So the stimulus and the response are on the same side. And that's intuitive, that's compatible. One difference in this experiment is we're not going to use the keyboard anymore to make responses, and for the stimuli, we now have these little buttons. We'll fire this up a little later if we have time. And then here are the stimuli. So you can imagine the left light turns on and you need to press the left button. So very easy. Now, a little bit harder is the contralateral mapping. You probably guessed we were going here. So contra is an opposite sides. So now on this block, the participant is told, well, if it's a left stimulus, make a right response. And if it's a right stimulus, make a left response. Now, importantly, in the contralateral mapping, there's a conflict during response selection. You've seen a left stimulus, and now you need to make a right response. And that's kind of the opposite of what's natural or intuitive or compatible. So this is going to take longer. It's not worlds difference. I mean, we can do this, but you will have a longer reaction time here. And just to reinforce, well, why is that? If we think about our 3 stages of information processing, when it is a compatible or easy response, such as the ipsilateral mapping, we see that response selection is short. So overall, we see a short reaction time. Now, in the contralateral mapping, we can think of that, or the other name for that is it's incompatible. That conflict during response selection increases the duration of response selection. And in terms of magnitude, by maybe about 100 milliseconds. And that's long enough that you'll feel a difference between these two mappings. So because response selection is longer, reaction time is longer. And the idea here is that these other stages, stimulus identification, response programming, they're the same. You know, identifying a left or right stimulus doesn't matter. You know, making a response with this finger or that finger, that doesn't make a big difference either. The change in reaction time here is because of the conflict during response selection. That is the general or short explanation of why there's a difference between these two things. But now I'd like to give you a stronger theoretical framework for what is happening in the brain that causes this 100 millisecond difference. And we're going to look at something called the dual process model. And it's a great explanation for the ipsilateral and contralateral mapping and why they're different. But the nice thing about this model, and we won't go into this module, but in the next module, it will explain those results as well, is it can explain most compatibility situations. You know, whether it's something very simple like the ipsilateral and contralateral mapping, or whether it's, you know, comparing maybe a Macintosh laptop to a PC laptop. Maybe not that applied, but it can explain a lot of experiments on compatibility. So this is what the model looks like, and you don't need to memorize this, and you don't need to display it in your presentation, but you can definitely apply this, and that's much easier to do than it looks at first glance. So what's happening here is we're looking at information processing in these sorts of tasks, and what happens is we do some initial stimulus identification. So we're going to see those same stages we've seen before, so this isn't completely new. What's new is that after some initial stimulus identification, there's some parallel processing in the brain. So there's 2 parts of the brain or 2 networks that are going to process the stimuli and come up with a response. So these processes or pathways, there's an automatic one and there's an intentional one. And I've tried to color code them consistently throughout the slides here. So the automatic pathway, we call it automatic because it wants to do the most natural, intuitive thing based on that stimuli. So in this, we'll apply this in a moment. So it says, okay, what is just the most reflexive thing to do in this situation? Okay, I want to do that, and I'm actually going to program that response. Now the intentional pathway, it says, okay, well, let's not just go with the most automatic, reflexive thing. Let's think about the instructions. So is this ipsilateral mapping? Is it contralateral mapping? It thinks about that. And based on spending some more time thinking about the task and the instructions, it selects a response. These 2 pathways meet up and they say, hey, do we want to do the same thing? And if they do, great. So think of it like 2 friends who are both solving a math problem. And this is your friend who's really good at math, and this is your friend who's not as good at math. So if they both independently solve the problem, they come together, they have the same solution, great. You know, that it's probably correct because both people came up with the same solution. So yes, if both pathways want to do the same thing, let's just go ahead and initiate that response that has already been programmed by the automatic process. And that's not a lot of stages. If you think about time down here, so you're going to have a short reaction time. Now, if those pathways come together and they say, oh, we want to do different things, or if the two friends say, well, I think the answer is 36, I think it's 47. Well, in that case, who are we going to trust? We're going to go with the intentional process. So think of this like your friend who's good at math. If you're the judge and one is good at math, has one answer, one is bad at math, has another answer, you would vote or you would bet on the student who's good at math. And your intentional pathway, it's kind of like the SMART pathway. It's thinking more deeply about the task and the instructions. So when there is a conflict, your brain will trust the intentional pathway. So we want to program this response. The problem is that the automatic pathway has already programmed a different response. So we need to start by aborting that response. We can then program the response selected by the intentional process. And then once it's programmed, we can then initiate it. If you see here, compared to when the pathways agree, we've added 2 steps. So our reaction time is longer. That may have seemed a bit abstract, so let's look at that within ipsilateral and contralateral mapping. So in the ipsilateral mapping, there are 2 situations, right? It could be left stimulus, left response, or right stimulus, right response. And basically the same thing would happen, but in this example, we'll just think about left stimulus, left response. So we have some initial stimulus identification. So your brain sees, hey, there's a left stimulus. And that information goes on these 2 pathways or to these 2 processes. So the automatic process, if it sees a stimulus on the left, it says, I want to press left. That's just the most automatic, natural thing. Something on the left, stimulus on the left, I want to make a response on the left. So I select left, I program left. The intentional pathway says, okay, well, hold on. What were we told to do? In this block, it's an ipsilateral mapping. There was a stimulus on the left, so we should select a left response. These 2 pathways meet up. Hey, do we want to do the same thing? Yep, we both want to make a left response. I've already programmed that response. So let's go ahead and initiate it. And we have a short reaction time. Here's our contralateral mapping. So the example could be a left stimulus that requires a right response, or it could be a right stimulus requiring a left response, but you get similar results from the pathways. And in this case, it's a conflict between them. So we do some early stimulus identification, and then this information goes to 2 networks in the brain. The automatic pathway, just like before, says, hey, there's something on the left, I want to make a left response. So I'm going to select the left response and program it. That's the most obvious, natural, reflexive thing to do. The intentional pathway says, well, what were the instructions? It's a contralateral mapping. So because the stimulus is on the left, I should make a right response. So I'm going to select a right response. They come together. Do we want to do the same thing? No. So we're going to trust the intentional pathway. But we've already prepared the automatic, the selection made by the automatic pathway. So we have to abort it. We're going to abort the left response. We're now going to program the response selected by the intentional pathway, and then we can go ahead and initiate, send it out to our muscles. So 2 extra steps, longer reactions. So in some ways, we don't need to worry too much about the boxes. We just need to think about that there's the automatic and the intentional processes or pathways. And in the ipsilateral mapping, in this case, the automatic response is left because the stimulus is on the left, but the intentional response is also left because the instructions are ipsilateral, so they're in agreement, short reaction time. For the contralateral mapping, because the stimulus is on the left, the automatic response is left. Now the intentional response is right because the participant knows in this block they're doing the contralateral mapping. So because they don't match, they have to go through a few extra steps, and we're going to see a longer reaction time here. Any questions about the dual process model? So that's the theoretical underpinnings to an explanation of compatibility effects. And they work through the ipsilateral contralateral mapping. Next module, we're going to look at the Simon task or the Simon effect, and it explains that. Another one, it explains the Stroop task. So if you ever seen where you have to name the color of a word, so the word will say blue, but the ink will be green. And you're supposed to ignore what it says and say the color it's written in. That's Stroop task. And you can also explain it with this dual process model. In Stroop, the easy version of the Stroop, well, an easy trial would be this, because here the word and the color it's written in are the same. So the automatic pathway wants to read the word. The intentional pathway says, okay, the instructions are to say the color, but they're both the same here. So they're in agreement, short reaction time. This our trial, this is the incompatible trial, where the automatic pathway says, I know how to read, I want to say green. And the intentional pathway says, whoa, slow down there. Say the color it's written. Okay, I need to say blue, almost like green. So they're in disagreement. And that's why you have to go through the extra steps. Has everyone seen this Stroop task before? That's a pretty common one. It's was public. Well, there's a bit of argument over when it was kind of earlier research kind of mentioned the idea, and then in I think it was 38 or 28, a researcher Riley Stroop, I think it was his name, actually kind of ran the experiment, and it happens to be the most cited study in experimental psychology. And there's kind of so much debate about it that a lot of people don't even want to touch it because so many people have very deep opinions about, how it works. I am also one of those people who does not want to touch it. I sometimes use it, but contributing to the theoretical understanding of it is a minefield. Shall we chat about running this experiment? Yeah. Keith.
So before you get next, ask a question about compatibility in other kind of motor control things.
Sure. Yeah.
So like a lot of friends who like play video games, and some people like to have the camera working.
Yeah.
So you put the analog stick up and the camera aims up.
Yeah.
But I like to do the opposite. I like to work as if it was like a plane flying, right? Whereas like I pull it down, it goes up, it goes up, it goes down. So could that be explained?
Yes.
By this kind of thing, like
Yes. And that's one of the examples I used to give in my class. So yeah, there's like normal and inverted, they're often called. I'm trying to remember the analogy because one, you're right, one is like how airplanes work.
yeah,
But the other
inverted
one,
is how hard.
I remember reading about it and people saying some people think of it as you're like literally moving your head. And other people think about it, it's like, no, you're moving the camera behind your head. So why do some people prefer one over the other? I usually like inverted, but I think it's because one of the first person shooters I played was GoldenEye. And it
Was inverted.
it was inverted, that was the default mapping. So that's when I got used to it, and I still kind of like it. But I don't know if you're like born with a preference.
Yeah, that was my question. Is it genetic? Is this like based on previous experience or?
Well, compatibility is kind of fun because there are some things that are inborn, like left stimulus, left response. We probably come out of the womb, wired with that mapping from genetic evolution. But other things, like I think the text will talk about light switches, right? And in was this thing?
Oh, yeah.
Yeah. So in the US and lots of North America, Brazil as well.
Yeah.
Maybe? So you think up is on, just like that's normally.
Oh no, that's the opposite.
Is it? Okay. So in Brazil and in Germany, down is on.
Down is on.
And that's just normal. But you don't come out of the womb with that expectation. It comes through experience. So we can definitely see both things at play. Yes, I don't know if some people are born, inverted gamers or not. Do you remember early first person Control, yeah.
I mean, I can't remember, I have Pro with Counter-Strike, so it would be mouse, so it wouldn't apply.
Yeah, different, yeah. I guess it's easier for me because like when I was young, they didn't really have first person games. So there's a definite point where they all of a sudden existed. Ooh, and actually the video I used to show in class about that was, I think it was Halo 2. Did you ever play that one? Yeah, Shelby did? Great. So do you remember at the start of the campaign where they play some cinematics and then Master Chief, they're like, oh, you know, we got your new suit, we just need to test it, look up, look down. So what they're doing is the game sees which way you press the controller, and then it automatically sets whether it's normal or
Good
inverted.
idea.
Yeah,
Yeah, so it's quite clever.
they did that with Halo 3 too.
Did they?
Good
Oh,
idea.
okay. Because I remember like as a kid, going, why am I doing this? And then
Yeah.
doesn't really work in like multiplayer if a friend comes over and picks up a controller, but I thought it was a good way to do it.
That's the only thing that I always struggle with, like me and my brother-in-law, we'll be playing the same game, like taking turns, you die, you pass the controller on.
Yeah.
They're like, oh shit, I have to change the settings.
Pause it, yeah.
Because he was like, okay, normal, we got on with inverted.
Almost needs a little button on there.
Yeah.
Okay, so here's the code. And like last time, all you need to do is change the participant number. And then this is for changing the condition. And here we just have 2 blocks or 2 conditions. So if you put in 1, it will run the ipsilateral block, and 2, it will run the contralateral mapping. Now the order to do those, because there's only 2, it's an easy counterbalance. And this is the sign up sheet. So participant 1 will do ipsilateral, then contralateral, and then participant 2 does the opposite, and so on and so forth. And again, I did add that column of when you want to present, because I thought it's possible your preference may have changed since last time. I guess I'll see if it's, well, I guess we only have 3 more modules, so we can probably always do that, not a big deal. So that will be in the lab, beside the computer, like before.
So odd numbers are HC first and even numbers are constant first.
Yes, correct. I don't know, I don't think there's any real logic to that, unlike our experiment, but
Which one do you like, regular, maybe, or inverted?
okay.
And it's like you can first and stuff.
Now,
Like
the
first and
name
right.
of the program, I think, oh, it's been cut off here, but the name of this code is compatibility.m. So to run the code in the command window, you just type in compatibility. Don't do the .m part, it doesn't like it. And okay, that's the output. So let's bring this up here. So I can show you what it looks like. The lights. These feel free to move so it's comfortable for you, but you should have the buttons and the lights aligned, so you know they shouldn't be angled. It's meant so that the buttons and lights align, but if you want this further or closer, then feel free to adjust so you're comfortable. Let's see here. I will run the ipsilateral block. Okay. Just booting up here. Okay. So there'll be a little warning that appears. That's okay. And then it will say press spacebar to begin or F2 to exit. So, you know, if you realize, oh, I ran the wrong block, you can press F2 to exit. Otherwise, press space. Now, what will happen is there'll be a 3-second delay, and then the trials are going to go. So, just like in the other experiments where you had to be vigilant, because if you're not responding, it'll just keep throwing them at you. So once you press spacebar, be ready to go. There are, I think, about 70 trials. I forget now, but you can look at the output files for those details if you want to know. So let's see here. I'm gonna start this. And I press, okay, so there was our first trial. So you get the warning light turns on here, so that's your warning, and then 1 to 2 seconds later you get a stimulus, and you need to press that button. And unlike what I'm doing, you should have your 2 fingers right on here so you can be as fast as possible. So, and this is the ipsilateral block, so right stimulus, right response. And you just need to press the button as quick as you can. You don't need to hold it down or anything. And then it'll just keep going. So it's quite, it won't take too long. Oh yes, it's telling me here that there are 80 tracks. Okay, see if I can stop it. Okay, there we go. And let me just see how long it took me to run the other day to give you a better idea. 21. So it looks like it's like 5 minutes to do each block. So the sign up is 15-minute chunks, so that should be fine. You can just sign in for one chunk or drop by. Questions about running the experiment? Yeah. So
yeah, are the boxes like always going to be connected to the thing?
yes.
Okay.
Unless
I don't have to worry about anything like that, like the wire.
No, I'll leave it all set up. Unless I forget.
What do we restrict?
So you can just kind of wherever is comfortable. I usually kind of do this. But yeah, I mean, if you want your fingers here or here, I mean, hovering for 5 minutes might be a little uncomfortable. But yeah, I usually kind of do something like that. Just as long as you've got your index fingers, on the buttons, not above, because that's gonna take longer than just pushing it a tiny bit. Any other practical questions there? So when you're done, again, I will share the data after the collection period is due, but you can go into the data folder, and a little different than last time, you're actually going to see a file. There's a file for every single trial. We're not going to worry about these. We'll talk a little more about them in our next module. But down at the bottom, you can see there's those 2 Excel files that contain all the information for the entire block. So it's like, I think like last time, it's called block output array. You'll have your participant number and then the condition number, 1 being ipsilateral, 2 being contralateral. So those are the 2 you want to grab. So I've opened one up here in Excel, and it's, they're going to be the same thing as last time, where you need to do the, data import. How many people had their data import in scientific notation?
Mine wasn't in sight.
Yes, Guy's was the weirdest. All of his data, and like he sent it to me, and it worked on my computer, but not on your computer. And we couldn't figure out why, but all your values were 10 million times too big.
Multiplied by 10. So I had to manually fix every single.
Yeah, so you had a value.
Not one each time. So I did a
Formula,
I still had to do it.
So here's what you'll see, and here just to, on this slide, there is an explanation of every column that you can use when you come back to this later, but it's very similar to last time. So here we have your trial number. This is your 4 period, and I've actually cleaned this up so it's just 2 decimal places. You might see several decimal places. This tells you the mapping. So for the condition 1, it will always be 1. Condition 2, it will always be 2. Ipsilateral, contralateral. This is the side the stimulus appeared on, so the light. Oh, is it a practice trial? So the first 16, like before, our practice trials, the other ones are all test trials. Here, this is the reaction time for the left button and the reaction time for the right button. And if we look at this trial, you might be like, well, why is there this weird value? So this means that you didn't actually press the right button, you pressed the left button. And on a good trial, there should just be 1 response. You shouldn't have pressed the other one. If you ever press both buttons, then you would have 2 reaction times, and it would say, hey, that's a recycled trial. which is the last column. Is it a recycled trial? So processing, very similar to last time, you can remove the practice trials, those first 16. When you look at the recycled trials, last time we just got rid of them, but this time I'd like you to do one extra thing, and that's look for recycled trials where you made an incorrect response. There's a few reasons a trial might be bad. It could be that you press the button before the go signal, or it could be that you press the wrong button, or that you press both buttons. So count, you don't need to count if your reaction time is too fast, but anytime you press the wrong button, which includes if you press both buttons, count those trials, because that's one measure we're going to report of errors. Because as you can imagine, errors are probably more common with the contralateral map. So once you've counted how many incorrect key presses you made, go ahead and remove all the recycled trials. You can sort them by stimulus side, and make sure to sort all the data with the special sort command. Don't just sort a single column. And then you can calculate your mean reaction time. So for the ipsilateral block, you'll get two means. I want you to find the mean for left stimulus left response and the mean for right stimulus right response. And then for the contralateral block, the conditions are a little different. So you'll have a mean for left stimulus right response because it's contralateral, and similarly right stimulus left response. So 4 values. And the way to arrange them to facilitate a line graph is in a table like this. So Excel can be a little bit picky about how you put the data when you try to make a graph. So I just thought I would, you don't need to struggle through this. This is kind of the way to do it, to make a line graph that appears in the conventional manner for displaying stimulus response compatibility. So put your data points in like that. And one thing you'll notice here is these are actually the ipsilateral blocks, ipsilateral mappings. So left stimulus, left response, right stimulus, right response. So it's maybe a little weird in that way because you might think that they should be together, but you want to do it like this. This will just make your life easier. And then these two, of course, would be the contralateral mapping. And we can already see this is like, I tried running through it once, and you can already see that my reaction time is shorter for ipsilateral than it is for contralateral, which is what we expect. So in your presentation, I'd like you to display just your own results. You don't need to display the class results, but yes, I will send those out if you want to compare to those in the discussion. So your chart should have this format. This is just the format we always use for stimulus response compatibility. You could plot these the other way. You can do that, but it is wrong. You don't want to do it. This is the convention. Put it that way. So on this axis, on the x-axis, you have a left response, a right response. You put your dependent variable on the y-axis. That's fairly normal. But we have a second variable we need to consider here, independent variable, the stimulus position, and the convention is that goes in a legend. Sometimes what I do in my undergrad class, we look at these, I actually draw little pictures to show what condition that is. Let me just give you an example of that. Because I've looked at these, so many of these, and I see this right away. I know what's happening, but if you can help thinking about these data. So, well, okay, we're going to go with all one color here, but I will use the different shapes. Usually I like to use both as redundancy. Also, if someone ever prints it in black and white, so they can still see this difference. And then even with my students, throughout the years, I've had different students who are partially colorblind. Most common it's red-green, but it can often be anything. So if I'm showing this and a student can't distinguish blue and orange, they can at least tell the difference between the square and the circle. Anyways, so we think about this condition. What is happening here? Well, we know it's a left response. So we'll draw, there's your left finger making a response. And which stimulus is it? Well, it's blue, so it's a left stimulus. So it's this condition, and that's a compatible condition. That's the ipsilateral map. Now, what about this dot? What does it represent? Well, it's still a left response. But now it's the orange square, so it's a right stimulus. So you can see that it is a contralateral map. So yeah, it makes sense that you're faster here and slower there. And you can do the same thing over here, and you'll find out that this is the ipsilateral mapping and that's the contralateral map. And the very typical stimulus response compatibility effect is a nice looking X. But it also, you know, if the patterns were the exact opposite, then it would still be an X, but it would be inverted. So it's actually important, you know, which direction, say, the blue line is in. And sometimes it's not a perfect X. It'll be interesting to see what your data look like, because sometimes it, you know, it can be a smaller compatibility effect, a larger compatibility effect. You might be really dominant with one arm or the other arm. So if you don't see a perfect X, that's not necessarily a problem. Questions on the conventional plotting of stimulus response compatibility? It's like, I want my data. Right? And then the other thing is the number of errors you make, the number of incorrect target responses. For my data, it was kind of boring. And I'm curious, maybe this may or may not be more interesting in your data. So for me, in the ipsilateral block, I didn't make any mistakes. And the contralateral, there was one trial I pressed the wrong key. So, you know, not too interesting for me. But maybe your individual data, or if not that, maybe the class data will be more interesting there. Key.
The counterbalance effect of this one caused potentially more errors on the ipsilateral. If you do the counterlateral first, and then you do that one first, and then you move to the ipsilateral block, which you think you find more errors because you're used to the one you just did.
It's just being
Or the opposite is not true.
yeah. Maybe. And that's something I can try pulling out. I mean, there'll only be 13 data sets, I guess. Well, I guess I didn't make their mistakes. I'm not saying I'm good at this. It's just, I don't know. This is what happens. Maybe when you're sleep deprived, you don't make very much mistakes. If we have more people, you can actually look. Doesn't matter which one you start with. I can try looking at that with just 6 and 7. Yeah, I guess the safest way might be, well, there's 2 options. You could, instead of saying, well, instead of just doing one and then the other, let's send you home, sleep, bring you back. So 2 different days. And then if you are still unconvinced, even with a counterbalance that, there may be a large influence, you do completely separate groups. So you'd say, I'm going to get 13 people to do only ipsilateral and 13 people only to do contralateral. There's a hit there to your statistical power. So then you almost you almost have to double recruitment, in that case. So it's you'd rather test 13 people on 2 conditions than 26 people each doing 1 condition, as you discovered in your thesis. All right. So I think we're almost at the end here. So just to summarize, reiterate here, for your presentations in your results, what I expect to see is a graph of your reaction time results in that format we looked at. And I'd also like to see a graph of your incorrect responses. And for that one, I think it's fine to just say ipsilateral this many, contralateral that many. I don't think you need to break it down into left hand, right hand, because I don't think there will be a lot of errors overall. So just total in one, mapping total in the other. And then, as I mentioned earlier, you do not have to present the class results. I know we only have so much time, and because I've asked you to do a second graph, I thought, okay, well, if I ask you to present more data, I kind of need to take something else out. So I thought I would get rid of the class data. The other reason for that is I think everyone should see a nice stimulus response compatibility effect. It's usually a large effect that you kind of see in everyone. When we do the Simon effect, that's not necessarily the case. So on that one, I'll put that requirement back in. But I will send it to everyone after data is due. I'm not trying to trick you by saying you can or you can use it if you want, but you don't have to. So you should have some sort of comparison interpretation that could be to the class data, that could be to the data in the textbook. Either is fine. That's either one is appropriate, and I guess one or the other, or a third option if something else inspires you. Just two important dates. So data collection will be due by the end of the day on Wednesday. The lab is available tonight. For those of you, I know about half you are here for a little while until your next class. So if you want to test yourself today, you can. We'll just bring this back to the lab after class. And then the next time, mandatory butts and seats in class will be for your presentations on Wednesday, October 13th. Okay, yeah. Any other questions in class right now? Otherwise, as usual, I'm around and let me know how I can help. So if you do want to test right now, give me 10 minutes to get everything back in place. Sure, that would be good, actually. There are a few too many things. And